Okay, so today we're going to be going over traveling waves. What you need for this lab are a slinky, a timer, a meter stick, your traveling wave machine, a snaky attached to a rope, and a student holding that snaky on one end, and a long tape measure. So David, how do we do this lab?
So first we're going to check the parameters that are important for a wave. Frequency, wave velocity, amplitude, etc. So looking at the wave machine first, the amplitude is the height of the wave. So if I want to alter the amplitude, this would be a small amplitude. The sticks aren't going up and down with much displacement, or bigger displacement, bigger amplitude. Now notice, can I change the speed of the wave? I'm going to send a pulse down. So there's a pulse traveling down. Once again, there's a pulse traveling down. Can I make that pulse travel down faster? Well, there it goes. Let me try to do, there it goes. I'm trying to make that pulse faster. I don't know how easy it shows on the camera, but that pulse is pretty much traveling the same rate every single time. What's the frequency? Is how frequently I go up and down to create these waves. So you're now looking from crest to crest or from the dips, trough to trough. And if I change my frequency of how frequently I go up and down, you're seeing the wavelengths, the amplitudes cluster together. So this is a much greater frequency. Or if I take a longer period of time, you can see what we're doing here now is I've got the distance from peak to peak is different than when I'm changing it to a more frequently, a shorter period of time. And those are the parameters that we're analyzing in this activity. How can we do it for a longitudinal wave? That's what our slinky is here for. And the pulses, the amplitude, where that compression is going. I don't know how easy this shows on film, but you're seeing that pulse travel. If I want to make that pulse go at one speed, let's see if I can make that pulse go at a different speed. I don't know how easy it shows, but it looks like that pulse is pretty much going down the same speed no matter what I do. And the distance from pulse to pulse, you can maybe see there's two pulses, would be our wavelength, and the amplitude would be how much that pulse is compressed. So there's not much of an amplitude, not much of a pulse. And then right there, it's easy to see the pulse, it's more compressed. That's the equivalent of the amplitude for longitudinal. And this is great frequency, sending multiple pulses down. And this is not so frequent, a longer period of time. And we can measure the rate of travel for those pulses, those waves, with our timer and our meter stick, which you can see as that pulse goes. Even though my hand is not tracking it well, that is pretty much going at the same speed. What happens when we connect one medium to another? Medium, this case being rope and the snaky, I'll do the same thing. I'll send a pulse down. It's not so easy to get that snaky to move, so I'll make a wave. And so now you're seeing pretty much half of a wavelength along the rope. And when I'm doing my half a wavelength along the rope, you can see that there's more, a shorter wave, right? More peaks in the snaky. So it's one wavelength, half a wavelength in the rope, and more than a full wavelength plus in the snaky. And I'll try to go more frequently, increase the frequency, and you're seeing now shorter waves in the snaky at great frequency, and less frequently, a longer period of time that even the snaky has there we go, even the snaky has a longer wavelength in it. And notice that I have a long wavelength in the rope and short wavelengths in the snaky. And don't forget to wear your safety goggles for this experiment.